Okay, third statement. Since the closure of Z in Y is a subset of the closure of Z in X, we have that the intersection of the closure of Z in Y with Y is a subset of the intersection of the closure in Z in X intersected with Y. Now, the intersection of the closure of Z and Y with Y is the closure of Z and Y, and this is a subset of the intersection of the closure of Z and X with Y. Now, let the collection of sets f sub I for I in some indexing set I be the collection of all closed sets in the subspace Y containing the set Z. Then the closure of Z in Y is the intersection of these sets. Now, by statement 2, we have that for every index I, there exists a set C sub I which is closed in the ambient space X such that f sub I is the intersection of C sub I with the set Y. And so the closure of Z in Y is the intersection of the sets C sub I with the set Y, which is the same as the arbitrary intersection of the sets C sub I intersected with Y. Now, since for every index I in the indexing set I, we have that the set Z is a subset of the intersection of C sub I with the set Y, which itself is a subset of C sub I, the arbitrary intersection of the sets C sub I is a closed set in the ambient space X containing the set Z and so the closure of Z in X is a subset of the intersection of the set C sub I, and hence the intersection of the closure of Z in X with the set Y is a subset of the intersection of the sets C sub I with the set Y. That is, the closure of Z in X intersected with Y is a subset of the closure of Z in Y. So we have demonstrated set inclusion in both directions. And so the intersection of the closure of Z in X with Y is equal to the closure of Z in the subspace Y. So fourth statement, since the interior of Z in the ambient space X is a subset of the interior of Z in the subspace Y, we have that the intersection of the interior of Z in X with Y is a subset of the interior of Z with Y intersected with Y. Now the intersection of the interior of Z and Y with Y is the interior of Z and Y. And so we have that the interior of z and x intersected with y is a subset of the interior of z in the subspace y. Now suppose that the interior of z and y is a subset of the interior of z and x, then the interior of z and y intersected with y is a subset of the interior of z and x intersected with y. And again, the intersection of the interior of z in the subspace y with the subspace y is the interior of z in the subspace y. And this is a subset of the intersection of the interior of z in the ambient space x with y. So in this case, we have that the interior of z in the ambient space x intersected with y is equal to the interior of z in the subspace y. So in general, the intersection of the interior of z in the ambient space x with y is a subset of the interior of z and y, and if the interior of z and y is a subset of the interior of z and x, then we have equality. So as an exercise, let y be a subspace of a space x. Let x be a point in the space y, and let the collection script b sub x be a neighborhood basis for the point x in the ambient space x. Show that the collection of the sets consisting of the intersection of b with y, where b is an element in the neighborhood basis for x in the ambient space x, is a neighborhood basis for the point x in the subspace y. Now, a set that is open in a subspace is not necessarily open in the ambient space. And similarly, a set that is closed in a subspace is not necessarily closed in the ambient space. So as a corollary of the previous theorem, we'll look at the conditions that guarantee that a set that is closed or open in a subspace is also closed or open, respectively, in the ambient space. So, corollary, let Y be a subspace of a space X, and let Z be a subset of the space Y if Z is open in the subspace Y, and Y is open in the ambient space X. Then the set Z is open in the ambient space X. And if the set Z is closed in the subspace Y, and Y is closed in the ambient space X, then Z is closed in the ambient space X. So proof, first statement, as the set Z is open in the subspace Y, Z is equal to the intersection of a set U with the set Y, where U is open in the ambient space X. So if the subspace Y as a set is open in the ambient space X, then the intersection of U and Y, which is the set Z, is open in the ambient space X, as it is a finite intersection of open sets. So second statement, as the set Z is closed in the ambient space Y, Z is equal to the intersection of a set C with Y, where the set C is closed in the ambient space X. So if the set Y is closed in the ambient space X, then the intersection of C and Y, which is the set C, is closed in the ambient space X, as it is an intersection of closed sets. So as a second exercise, let Y be a subspace of a space X, and let Z be a subset of the space Y. Show that the subspace topology on Z relative to Y is the same as the subspace topology on Z relative to X. In other words, show that if Y is a subspace of X and Z is a subspace of Y, then Z is a subspace of X. Now let X be a simply ordered set with the order topology, and let Y be a subset of X. Then the simple order relation on X, when restricted to Y, makes Y a simply ordered set. However, the resulting order topology on Y is not necessarily the same as the topology that Y inherits as a subspace of X. So new definition. Let X together with the relation less than be a simply ordered set. A subset Y of X is convex in X if and only if for every pair of points A and B in the set Y with A less than B, the entire interval the open interval from A to B of points in X lies in the subset Y. So as an example, let Y be the union of the half open interval from 0 to 1 with the singleton containing 2, and let this be a subset of the reals. Then the set Y is not convex in the reals, since 0 and 2 are points in the set Y, but the open interval from 0 to 2 is not contained in Y, and this is an example of a subset of the reals for which the order topology on Y is not the same as the topology Y inherits as a subspace of the reals. So notice that all rays and intervals of the simply ordered set X are convex in the set X. Okay, so new definition. Let X together with some topology tau be a topological space and let script B be a basis for the topology, a subbasis script S for the topology is a collection of subsets of the space X such that every element in the basis is a finite intersection of elements in the collection script S. That is, for every element B in the basis script B. B is a finite intersection of elements S sub I, where each element S sub I is in the collection script S.